So in this lecture, I will discuss the open mapping principle, which is a very important theorem. So the theorem which I want to prove in this lecture and to discuss some of its consequences is the following. You have M, a bounded linear operator from X to Y, where X and Y are two Banach spaces. And I will assume that M is surjective, which is also called onto, and which means that for all Y in Y, there exists X in X, such that Mx is equal to Y. So for any point Y in Y, we can find X in X, such that the image of X is equal to Y. So these are the assumption. M it's a bounded linear operator which is surjective, and what I claim is that there exists a positive radius R such that the image of the open ball centered at the origin with radius 1 contains the open ball of radius R. So if M is surjective, we will prove that there exists a strictly positive radius such that the image of the ball of radius 1, the open ball of radius 1, contains the open ball of radius R. So the proof of this theorem, it's based on the Baire principle, which I already discussed, but I will remind what I need in the proof of this theorem to have a self-contained proof. So first, the definition. A topological space S, so S a topological space, is said to be Baire if the following property holds for all sequence Gn of open sets and dense, so open dense sets, then the intersection of Gn is dense. So a space S will be said to be Baire if it has this property for all sequence Gn in S, which are open and dense. So if you take a family, a countable family of open dense sets in S, then its intersection is dense. And we proved in a previous lecture that if you S is a complete metric space, then it's Baire. And I'm going to use this property of complete metric spaces. Right? If S it's a complete metric spaces, then it is a Baire space, so it has this property. And now a remark. Assume that S is a Baire space, and consider a sequence Fn of closed sets So consider a sequence of closed sets and assume that the union of these closed sets is equal to the space, the old space S. So we started from a Baire space S, and we have in this space a sequence of closed sets whose union is equal to the old space. Then what I claim is that there exists N, and there exists an open set G such that G is contained in Fn. So we can find n and an open set G such that G is contained in Fn. And why is that so? Well, let me define Gn as the complement of Fn. So since Fn it's a closed set, Gn are open sets. And now, if we take here the complement, since the union of Fn is equal to S, if I take the complement of this union, it's empty. Well, but the complement of the union of Fn, it's the intersection of the complements of Fn, but the complements of Fn are Gn. So the intersection of Gn is the empty set. So we have a sequence Gn of open sets such that the intersection is empty. Well, this means, since S is a bare set, that these sets Gn cannot be all dense. Because if the Gn were all dense sets, the intersection will be dense, but the intersection is empty, which is not dense. So we know that there exists, so this implies that there exists a Gn which is not dense. There exists one of these sets which is not dense, because if they were all dense, the intersection will be dense, but we know that the intersection is not dense. So there exists a Gn which is not dense, but what it means that it's not dense? Well, it means that there exists a point x in S and a radius r, so a ball centered at x with radius r, such that the intersection is empty. So the intersection of this ball of radius r centered at x with Gn is empty. Right? If Gn is not dense, we can find such a ball. Well, but what is this saying? Now recall that Gn is the complement of n. This is saying that, let me write it here, because I'm almost finishing. I don't want to erase everything. So the intersection of Bn with Fn complement is empty. But this means that Bxr, it's contained in Fn. Right? Bxr, it's equal to its intersection with Fn. Union, its intersection with the complement is empty. This means that Bxr, it's equal to Bxr intersection Fn, and this means that Bxr, it's included in Fn. And this is exactly what we wanted to prove, right? We wanted to prove that there exists an n such that there exists an n and an open set G. Here is what I wanted to prove, so that there exists an n and an open set G. The open set G here, it's this open ball of radius r centered at x, such that this ball, it's contained in Fn. This is exactly what we proved. And this is what I'm going to use in the next step, in the proof of the theorem I just stated, is that, well, if we have a sequence of closed sets such that the union is equal to the whole set, then I can find n and an open set G such that G is contained in Fn. This is exactly what we just proved. So I stated again the theorem. We have a bounded linear operator which is surjective, and we want to show that there exists R strictly positive such that the image of the open ball of radius 1 centered at the origin contains the open ball of radius r and centered at the origin. The proof of this theorem is divided in several steps. So the first step, step 1, I claim that there exists n larger than 1 and an open set G included in Y such that G it's included in, you take the image of the ball of radius n at the origin, you take the image of this ball and you close that set. And I claim that, well, I can find n and an open set G such that G is contained in this set. So the proof of this claim, it's based on the bare principle, which I just stated. So Y, it's a Banach space, so it's complete. And, well, it's a normed space, so it's a metric space with the metric obtained through the norm. So Y, it's a complete metric space, so it's a bare space. Now, I know that M is surjective, so this means that Y, it's contained in the union for n larger than 1 of B0n. Right? Because the image of these balls. So I take a ball centered at the origin with radius n, I take its image, and I claim that Y, it's contained in this union, and this is clear because Y, it's surjective, so if you take any point Y in Y, you know that by the assumption that M is surjective, you know that there exists X in X such that Mx it's equal to Y. But now, well, X belongs to one of these balls because, well, n it's increasing to plus infinity, so X belongs to one of these balls. So Y, this point Y, it's contained in the image by M of one of these balls. And this proves that Y, since this holds for all Y, this proves that Y is contained in this image. And of course, I'm allowed here to take the closure of that set. So this is even weaker than the previous statement. So we just proved that Y it's contained in this union. Now I will use the previous result. These are closed sets. Y it's equal to the union of these closed sets. Y it's a complete metric space. So by the Bare's principle, I know that I can find n and an open set G such that G it's contained in one of these sets. So this proves the first step of my argument. So step 2 is that there exists M larger than 1 and R positive such that the ball of radius R it's contained in the image of the ball of radius M centered at the origin, and I'm taking the closure of this set. So now I'm claiming, well, that I can find M and R such that this ball is contained in the closure of the image of that ball. And I will start, of course, by what I proved already. So G it's an open set, so I can find a ball of radius R and centered Y contained in G. Right? Since G it's an open set, it's a non-empty open set, I can find this ball. So what I know is that B, the ball of radius R centered at Y, it's contained in the image of the ball of radius N, and I'm taking the closure of that set. Now, well, M is surjective. So here I have Y. So there exists X such that Y it's equal to Mx. So actually what I have is that the ball of radius Mx R it's contained in the closure of the image of the ball of radius n. And so I have two balls. This one is contained in the image of that one, so I'll just translate them to the origin, back to the origin. So what I claim is that by translating this inequality, what I get is that the ball of radius r centered at the origin and not at mx anymore, it's contained in the ball, the image of the ball, centered at minus x n. Right? I leave it to you to check that this inequality follows from this one. This one is telling me that all these points are contained in the closure of these points. Now, if I translate these points by mx, the translation of these points are contained in the translation of these points. The translation of these points are, well, the translation of the closure is the closure of the translation. And once I have that this point is mx, I can insert it here because the image of the translation, it's the image translated. And so we get this inequality from this one. I leave it to you to check. Now, my argument is that if you consider the ball b minus x n, this ball, it's contained. I want here in my claim a ball centered at the origin, so I'll just say that this ball is contained in a larger ball centered at the origin. So what I claim is that this ball is contained in a ball centered at the origin and with radius given by n plus the norm of x. Okay, so I also leave it to you to check that this inequality holds. And therefore, I can take here m sufficiently large, so m larger than n plus x, to get that this ball is contained on that one. If this is true, then the image of this ball is contained in the image of this ball, and this closure is contained on that closure. So what I just proved is that this set is contained in the image of the ball of radius m centered at the origin and the closure of that set. So we proved that indeed there exists a strictly positive R such that the ball of radius r centered at the origin is contained in the closure of the image of the ball of radius m. And this is exactly what I claimed in step 2. Now, step 3 is almost the same statement. I want to show that there exists a p larger than 1, or I want to replace m by 1. So I want to say that there exists r positive such that the ball of radius, and let me call that s, the ball of radius s, it's contained in the ball of radius 1, and I'm taking here the closure. And this is simple consequences of the previous inequality. I know that the ball of radius r is contained, so I claim that this implies that the ball of radius r divided by lambda, it's contained in the image, and here I'm just using the linearity of m. That is holds for all lambda positive, and I leave it to you to check this inequality. We know this one. By using linearity of m, we can conclude from this inequality that this inequality holds for all lambda. So by applying it to lambda equal to m, what I get here is that b0, let me call s r divided by m, we get that this is contained in the ball, the image of the ball of radius 1 and the closure. And I can further apply that again to this inequality by dividing S by 2k. So if I take a non-integer k, a positive integer k, what I get is that bs divided by 2k, it's contained in 1 divided by 2k and the closure. So up to this point, we proved that there exists a strictly positive S for which this inequality holds, and actually not only this inequality, but we can also divide it here by 2 to the power k, here by the 2 to the power k, and this holds for all k larger than 1. So this is the conclusion of the third step. Up to this point, we proved that there exists S strictly positive such that the ball of radius S is contained in the image of the ball of radius 1. The problem is that we want to show this inclusion, so without the closure of this set. So what remains to be done in this proof is to remove this closure to get what we want, and this is the last step in the proof. So now what I will prove is the following. I'll prove that B0S is contained in the image of B02. And so this is what I'm going to prove. So let's take Y in B0S. Since Y belongs to B0S, and B0S, so take this inequality with k equal to 0. For k equal to 0, and this is what we proved up to now, we know that the ball of radius S, it's contained in the closure of the ball of the image of the ball of radius 1. So we know from, since it's contained, we can approximate this point by a point in this set. So there exists x0 in the ball, in the image of the ball of radius 1, such that, well, the image of this, there exists x0 in this ball, such that the image of x0, which belongs to the image of this ball, approximate y as well as we want. So x0, I wanted to approximate y by r divided by 2. So the distance between the image, of x0 and y, it's bounded by r divided by 2, right? We know that this set, it's contained in the closure of that set, which means that any point in this set can be approximated by a point in this set without the closure. So we consider a point, y, and we are approximating it by mx0, where x0 belongs to this set. Now, if I look at this point, y minus mx0, it belongs, well, its norm is smaller than r over 2, so it belongs to the ball of radius r over 2, centered at the origin, the open ball, because this difference is bounded by r divided by 2. Now, I look again at this inequality, but now with k equal to 1. So I know, and here I'm writing r, but it's s, I'm sorry. So now I look at this inequality, but with k equal to 1. So this point belongs to this ball. So this ball is contained in this closure. So since y minus mx0 belongs to the ball of radius s divided by 2, I can find x1 in the ball of radius 1 over 2, such that the point y minus mx0 it's approximated by mx1 as well as we wish, and so we will require this difference to be bounded by s over 4. And now you see what I have in mind. I have now a new point which belongs to this set with k equal to 2, and I can repeat my argument so I can find a sequence xk. So xk belongs to the ball of center of the origin and with radius 1 over 2k, and such that y minus m of x0 plus x1 plus xk, so that this quantity is bounded by s divided by 2k plus 1. Right? This is exactly what we proved for k equal to 0 and k equal to 1, and by induction you can prove that for all k. So this is what we have. So by induction we construct this sequence. So now what I claim is that x0 plus x1 plus xk converge to some point x, which I will represent as the sum of xj for j larger than 1. This is clear because the norms of xk are bounded by 1 over 2k. So this means that this sequence is a Cauchy sequence. And therefore, since the space X it's complete, it converges. And I'm representing its limit by this infinite sum, so it converges. The norm of this, of X, since it converges, it's the limit of the norms. But the limit of the norm, this is bounded by the sum of the norms. And x1, I'm starting from x0, sorry, so here is x0. And x0 belongs to the open ball. So the norm of x0 is strictly bounded. So this is bounded by the limit in k of 1, because the norm of x0 is strictly bounded by 1 plus 1/2 plus 1/4, and this is equal to 2. This limit is equal to 2. So we know that the norm of x is strictly smaller than 2, so that x belongs to the ball of radius 2. So we proved that this sequence that we constructed, the sum of this sequence converge, and converge to a point x, which belongs to the ball of radius 2, the open ball of radius 2. And I claim, well, since this sequence converges to x, and m is continuous, that the image of m converges to the image of x, but mx by linearity, mx0 plus x1 plus xk is the sum of mxi, and the sum of mxi, actually here I wrote m applied to all these points, the distance of these, of y, it's smaller than s divided by 2k plus 1. This expression, it's converging to mx, as we have seen, and therefore y minus mx has norm equal to 0, which means that y is equal to mx. So let me make this argument slightly more comprehensible. So I want to estimate y minus mx and say that this is equal to 0. So by the triangle inequality, this is bounded by y minus mx0 plus xk plus m x0 plus xk minus mx. X0 plus xk is converging to x. M, it's continuous. So this quantity here, it's converging to 0 as k converge to plus infinity, because x0 plus xk is converging to x. On the other hand, this quantity here, it's bounded by s divided by 2k plus 1, which is also converging to 0 as k goes to infinity, and which means that this quantity here is 0, which means that y is equal to mx. So what did we do? We considered a point y in this ball, and we found x in this ball such that y is equal to mx. That is to say, we proved that the ball of radius s, centered at the origin, is contained in the image of the ball centered at the origin with radius 2. And this is exactly what we wanted to prove, because, well, now we can divide both sides by 2, and we get a strictly positive radius such that the ball of radius r is contained in the image of the ball of radius 1, and this is exactly what we wanted to prove. So I just wrote the theorem we proved, so that if we have a bounded linear operator from two Banach space, x to y, which is surjective, then we can find a strictly positive r such that the ball of radius r and centered at the origin is contained in the image of the ball of radius 1 and centered at the origin, and all these balls are open balls. Now I want to prove the open mapping principle, which is given the name of this lecture, which reads as follows. So we have, under the same assumptions of the previous theorem, which is M, a bounded linear operator from two Banach spaces, which is surjective. Now what I want to prove is that this operator maps open sets to open sets. So this means that if I have an open set G in X, its image, Mg, it's an open set in Y. So this is what I wanted to prove. So let's prove this theorem. So let me take G in X, an open set, and I want to show that Mg is open. Mg, which is a subset of Y, is open. So to prove that Mg is an open set, what I have to show is to fix a Y in Mg, and I have to show that there exists a positive S such that the ball, the open ball centered at Y and of radius S, it's contained in Mg. So I fixed Y in Mg, and I want to prove that there exists S such that the open ball of radius S centered at Y is contained in Mg. So let's fix this Y. Since Y belongs to Mg, Y it's equal to Mx for some x in G. Now G it's an open set. So since G it's an open set, we know that there exists an epsilon positive such that the ball of radius epsilon around x is contained in G. So this is what we can deduce from the fact that G is open and that Y it's equal to Mx. Now let's turn to one of the consequences of M being surjective is that the existence of this strictly positive R. So we know by the previous theorem that there exists this strictly positive R such that the ball of radius R it's contained in the image of the ball of radius 1. So now if I multiply, I use linearity and I multiply both radius by epsilon, I get that the ball of radius R times epsilon it's contained in the image of the ball of radius epsilon. So I leave it to you to check this inequality. I claim that this inequality is very simple consequences from this inequality. Right? You want to show that any point here is contained in this set, and you use this fact and the linearity of M to prove that. So once you reach this conclusion, now I want to translate these sets to Y. So what I want to do, it's, since this set is contained in that one, the translation of this set is contained in the translation of the other set. So Y plus B0 R epsilon, which is the translation of this set by Y, it's contained in Y plus MB0 epsilon. Well, the translation by Y of this ball, it's simply the ball centered at Y and of radius R epsilon. On the other hand, Y is equal to mx, so I can replace Y by mx. Now I can use linearity of M to say that mx plus the image of this set by M is actually the image of x plus B0 epsilon. And finally, well, that the translation by x of this ball, it's a ball centered at x. So that this is equal to M of B x epsilon. So this is equal to that. So what we proved is that actually this set is contained in that set. So I will rewrite this inequality here. So what we proved is that the ball centered at Y and of radius R epsilon, it's contained in the image by M of the ball centered at X and of radius epsilon. Right? So the consequence of all this argument is this fact. And here what we did, it's simply we played with the linearity of M to replace R by R epsilon and 1 by epsilon, and then we translate everything by Y. Once we reach this conclusion, the proof it's finished because, well, we know that the ball of radius epsilon at X it's contained in G. So the image of this ball it's contained in the image of mg. And what did we prove? Well, we proved that the ball centered at Y and of radius R epsilon it's contained in mg. And this is exactly what we wanted to prove. Right? We wanted to prove that there exists a strictly positive S such that the ball centered at Y and of radius S, it's contained in mg. We proved that with S equal to R epsilon. R is the constant coming from the previous theorem, and epsilon, the strictly positive constant coming from the fact that G is an open set. So this proves the theorem. So now let's prove a second consequence of the previous theorem. The first theorem I proved in this lecture is, let's assume that M, now it's a bijection. So again, we have two Banach spaces, X and Y. We have a bounded linear operator M from X to Y. But now I'm assuming that M, it's a bijection. So it is surjective and injective. So surjective, remember, means that for all Y, we can find X such that Mx it's equal to Y. So this is the fact that it's surjective. And now I'm assuming also that it's injective, which means that if Mx1 it's equal to Mx2, then x1 it's equal to x2. So M it's 1 to 1, and the image of M it's the whole space Y. So once you have a bijection, you can define the inverse. you can define m minus 1 from y to x. And, well, how you define that? You take y, so you know that there exists an x such that mx is equal to y. You know that it's x, it's unique because m it's injective. And what you do is you send y to this x. Right? So whenever you have a bijection, you can define the inverse. So this is, I guess you all know that. Of course, since what I claim is that since m it's linear, then it's easy to check that m minus 1 it's linear. So m minus 1, it's a linear operator from the Banach space y to the Banach space x. That's fine. What I claim and what this theorem says is that m minus 1 is actually bounded. So I want to prove that the inverse of m, it's a bounded operator. We know, well, it's easy to show, and I leave it to you as an exercise to show that it's linear. And what this theorem states is that actually m minus 1 is bounded. So, proof. So let's prove that m minus 1 is bounded, and let's start from the main property. So we know that there exists, since m it's a surjective, we know that there exists a strictly positive R such that B of 0 R, it's contained in the image of the ball 0, 1. Now let's take y in y such that the norm of y it's R divided by 2. So this means that y belongs to this ball. So this means that there exists x in the ball of radius 0, 1 such that m of x it's equal to y. Right, this inclusion tells you that whatever point y with radius with norm equal to r over 2, you can find the point x in the ball of radius 1 such that mx it's equal to y. Now let me take a z in y. I can always write z as an element with norm equal to r over 2 times a number. So let me write z as z divided by the norm of z. So this new element has norm equal to 1. So if I divide it, I have to multiply that by z. Now I want to make this element which has norm 1 to have norm r divided by 2. So let me multiply that by r divided by 2. And let me therefore divide that by r over 2. So I can always express z as this product. So this element which has norm equal to r over 2 and times this scalar. Now, let me call that y. Y has norm equal to r over 2, so I know that y is equal to mx. So I know that z it's equal to mx times 2 times the norm of z divided by r, where x belongs to the ball of radius 1. So I know that I can express z as mx times this scalar, where x it's an element of the ball of radius 1. So now if I apply m minus 1 to both sides, what I get is that m minus 1 of z it's equal to m minus 1 of this element of y, but m minus 1 it's linear, so m minus 1 this is a scalar, so it gets out. And I get m minus 1 of m of x, but this is x. So I get that m minus 1 z, it's equal to 2 times the norm of z divided by r times x. If I take the norm now on both sides, well, this is a scalar, so it gets out. And I get the norm of x. But x, it's an element of the ball of radius 1, centered at 0. So the norm of x, it's bounded by 1. So this is bounded by 2 times the norm of z divided by r. And we have here that for all z in y, the norm of m minus 1 z, it's bounded by 2 divided by r times the norm of z. So this tells us that m minus 1, it's a bounded operator. So it's a bounded linear operator. And that the norm of m minus 1, it's bounded by 2 divided by r. So that proves that indeed, if m, it's a bounded linear operator which is a bijection, its inverse, it's also a bounded linear operator.